Okay, can everyone hear me okay? Yes. Great, all right. Hi, I'm Stephan, and you guys are really far away, so feel free to come closer. This talk is going to be all about dependent types. It's going to be a little bit dense. We only have 10 minutes, so we'll do our best and see how far we get. All right. Who knows what dependent types are? I guess a lot of you. Why are you here? Doesn't make any sense. All right, well, let's talk about the lambda cube. So actually, there's three things for today. I want to talk about the lambda cube, which is like kind of where dependent types come from, and we'll talk about the theory of dependent types. And then the reason why dependent types are interesting is really because of this thing called the Curry-Howard isomorphism. This is like one of the most fundamentally amazing ideas in computer science, in my opinion. So I'm really excited about it. And then at the end of the talk, I'll just give you a taste of Coq, which is a proof assistant and also a programming language that has dependent types. OK. So what's this lambda cube thing that I mentioned earlier? Well, if you were here for the past 2 or 3 talks, they were all about the lambda calculus, or mostly at least. So you should probably know what it is by now. But if you don't, it's really simple. It's just basically the kernel of every functional programming language. There are only functions in this language. So this, on the left, we can see the syntax for expressions in the language. This middle bullet point is how you write a function in the lambda calculus. And then the bullet point below that is how you apply a function to another function. OK. Any questions about that? I think, cool, everyone gets it. And the only kinds of types in this language are just the types of functions. OK. So system F is what happens when you add a polymorphism to the lambda calculus. I'm talking about the simply typed lambda calculus, by the way. So system F is what happens when you add basically functions from types to terms. So these are like, the simply typed lambda calculus is functions from just terms to terms. And if you have functions from types to terms, that's what we call polymorphism, or parametric polymorphism. So an example of this is like, say you have a concat function that takes 2 lists of any type A. Doesn't matter what's in the list as long as it has the same type for both lists. You can concatenate them. That's a polymorphic function. So you can write that in system F. All right. System lambda omega, what's that? So this is what happens when you add type operators to the lambda calculus. By the way, everything in blue is like stuff that we're adding on top of the simply typed lambda calculus. OK, so type operators are something like list itself. You know, like in a programming language, you have list of some type, list of ints, or list of bools. List by itself is a type operator that takes another type. And you can think of it as a function from types to types. OK, so we have functions from terms to terms, and functions from types to terms, right? That's system F. And now we have functions from types to types. So you might be thinking, well, there's one more possibility we haven't really considered, which is functions from terms to types. And those are dependent types. So the easiest way to formalize dependent types, this is called the first order dependent type theory system LF. Looks like this. It's quite small. It's not complicated. It basically just lets you have functions that take an ordinary term and return a type. So you can do all kinds of mind-blowing things once you have this capability. You can have the type of lists of length n, where n is a variable in your program. You can have the type of sorted lists or prime numbers, or basically any mathematical proposition you can think of. You can express in this language. OK, so well, now you know what dependent types are. But let's talk about why they're cool. All right, so the Curry-Howard isomorphism is basically this really deep correspondence between types from programming languages and propositions from logic. And so here's some of the correspondence. I've just written out a little table here for you. So on the left, you can see things that come from type theory. So we have function types, right, just arrows. And on the right, that corresponds to implication in logic. So a function that takes, has the argument type A and return type B is kind of like a proof that A implies B. OK, so a product type on the left corresponds to logical conjunction. So if I have a proof of A and a proof of B, then, well, I have A and B. And similarly, a sum type is like disjunction in logic. So if I have a, like in Haskell, if I have an ADT, like it's either an A or a B. It's one of those two, but not both. Well, that's like logical disjunction. And dependent types are next. So dependent types are how you add quantifiers to the logic. So if you don't need quantifiers, if you're just doing propositional logic, that is, not predicate logic, then you actually don't even need dependent types. You can do all this stuff in Haskell, just vanilla Haskell. But you can't actually do a lot in just propositional logic, so that's why this is useful. Okay, so for the last part of the talk, I just want to talk about Coq, which is my new favorite thing ever. I've been getting into this. So Coq is a programming language. It means rooster in French. And it kind of looks like ML family functional programming languages. So if you're familiar with like Haskell or OCaml, this syntax I think should be pretty familiar to you. So an inductive data type, which we're defining on the left, it's kind of like a GADT, a generalized algebraic data type in Haskell. Who knows what GADTs are? About 60% of you? That's pretty good. Okay. So it's like a GADT, but it also supports dependent types. And so here we're just defining a type called day. And there are 7 constructors, one constructor for each day of the week. And on the right, we have a function called next weekday, and it takes a day, returns the next weekday. It's a very easy function to write, but it turns out that this is really all that Coq gives you. You have just inductive data types, and you have functions that can pattern match and recurse on those data types, and not much else. And somehow, just with that foundation, you can actually kind of express all of mathematics, which I think is really mind-blowing. I'll show you how some of that works. Okay. So true, if I want to define a true proposition, well, it's just an inductive data type that has one constructor. In fact, you could say any type that has is inhabited, that means there are values of that type, is a provable proposition. In other words, you can say it's true. We can also define false to be the empty inductive data type. There are no constructors. You cannot make an instance of this type. It's impossible. Okay. I can actually define and. You'll notice that all these like logical connectives and these things that you think would be kind of built into a logic are actually just, you define them yourself in Coq. I mean, they're in the standard library, but they're defined this way. So and is really just an inductive data type that has one constructor called conj, which means conjunction. This is GADT syntax. So basically, if you have a P, which is a proposition, and if you have a Q, well, then you have and P and Q. You know P and Q. OK, great. So OK, using those inductive data types that we've defined, we can define if and only if. And it looks like this. If you have the conjunction of P implies Q and Q implies P, then you know that P if and only if Q. And by the way, this arrow, so it means both implication and also just function arrow type. It's the same thing in this logic. So that's why it's really simple and elegant. OK, so or, I can define or, and it's kind of like and, but it actually has 2 constructors. But otherwise, it's a very similar construction. Not is defined kind of interestingly. This might be new to you if you haven't seen intuitionistic logic before. But basically, we're saying that not A is actually defined as A implies false. So if I can prove that A implies something that's not provable, then, well, A can't be true. OK, so here's well, this is actually the first example of dependent types that we've seen. This is the proposition that 2 objects are equal. So that's the for all there is we're actually quantifying over terms. But this thing is a type. So that's dependent types. OK. Just really quick, so I won't explain this because I think it'll be obvious, but this is how you can define the natural numbers in Coq. You have just 2 constructors, 0 and then the successor of another natural number. And we can define this inductive data type, or this proposition called even, which is predicated on a natural number. So you can only prove this if the natural number is actually even. It's defined this way. It's kind of confusing because you might think, well, is even a function that like returns a bool that tells me if a natural number is even? No. Bools are not the same as propositions. I think this confused me for a long time when I first learned Coq. So this is the type that expresses the proposition that a natural number is even. It's not a Boolean. OK. Coq actually has a tactic language, which allows me to prove things using this kind of like scripting. It's much easier than writing out the proof terms by hand, but I could do that if I wanted to. So here I can prove that 2 is an even number. I think we're actually just about out of time, so I'll just jump to the end. So thank you. If you have any questions about dependent types, feel free to just catch me in the hallway. I'll be around. So yeah.